So thank you all. This is our first poster Pops Talk session. So the way this will work is we have the poster presenters grouped in groups of 2 or 3. We have them promoted to panelist mode. They'll each have about 3 minutes to just say anything they want to, pitch their poster, and then we'll have time for questions for them as a group, and then move on to the next group. So if you have questions for any of the speakers while they're talking, just please put them into the Q&A. And then we'll get to them during the discussion part. So without delay, Benjamin, the floor is yours.
Hi, my name is Benjamin Fields. I am a new post-bac researcher at NASA Goddard Space Flight Center. And my poster was about a project that I did looking for lasers in the HARPS spectroscope observations. So going into archival spectra of a bunch of stars. These are spectra that are taken at very, very high resolution. Nominally or originally to look for Doppler shifts that are indicative of exoplanets. But serendipitously, it's also a great instrument to look for lasers. So from our initial list of candidates, we ruled out a wide gamut of different false positives, ranging from cosmic rays, instrumental artifacts, stellar flaring, atmospheric air glow, because the atmosphere also produces its own emissions, and also some sources that were unknown but terrestrial ultimately, like we found that they were in our own atmosphere. And then we got to a final list of about 3 candidates that we have not been able to explain prosaically, one of which is especially of high interest. It comes from GJ317, which is a middle-aged red dwarf. And we know that it does actually have 2 Jovian planets in the outer part of its solar system. And it's very high metallicity, so it might maybe have Earth-sized planets too. We don't know. But that candidate remains very interesting and warrants more follow-up. And so that's where I'm at now. And yeah, it's exciting when you find an anomaly that you're not able to explain in a prosaic way. And so what we're trying to do now is do more follow-up to see what other explanations are out there, or if it might eventually shake out to be a technosignature. We don't know. So that's kind of the long and the short of it on my project. How am I doing on time?
You're great. That's 2.5 minutes. So
perfect.
Okay.
And yeah, watch the whole poster for the details. I highly recommend. Thank you.
Thank you, Benji. I highly recommend you check out his poster and all the posters too. Hopefully easy to find. So Mitchell, take it over. Thank you.
Yes, hello everyone. My name is Mitchell Eiser. I'm a PhD student at the University of Oxford. On Monday, Sarah Seeger gave us an excellent talk about why SF6 and NF3 could be exemplary technosignatures. However, she did mention that in order to distinguish SF6 from other trace gases in the atmosphere, we would need high-resolution spectroscopy. While high-resolution spectroscopy in the 9 to 15 micron window she was talking about is still a long way away, our near to mid-infrared capabilities are about to take a huge step up. The Extremely Large Telescope will come online in 2030. And with its high-resolution spectrograph METIS, we will finally be able to make observations of the atmospheres of nearby rocky exoplanets, like Proxima Centauri b. We simulated highly idealized METIS observations of an exoplanet with elevated levels of SF6 to determine if SF6 is, in fact, if the features of SF6 within METIS's 3 to 5 micron observation window are strong enough to be detectable. In these idealized simulations, we do find that SF6 is indeed detectable, only for extremely high abundances, bringing us back to that 100 parts per million figure we've heard before for low-resolution spectroscopy with JWST. This means that even with the power of the ELT, we'll only be able to observe deliberately released gases, for example, as part of a terraforming effort. We are currently working on simulations including all different instrument effects we expect from METIS to get the most realistic image of how well we will be able to do this. If you're interested in any of my work, please have a look at my video poster or come and have a chat with me.
Okay, thank you. Everybody is staying under time, which is great. We'll move on to Cal then, and then have time for questions. Not hearing you, unfortunately, Cal. Yeah.
Can you hear me now?
Yes.
Okay, sorry about that. My mic was muted. Just to introduce myself again, I'm Cal White. I'm a PhD student at the Florida Institute of Technology, and my work in the past couple of years has been revolving around the potential habitability of white dwarf exoplanet systems. And the poster work here is sort of an initial preliminary steps into the technosignature world. And the long-term stability and outlook for detection of exoplanets and rocky worlds around white dwarfs has really been what's motivated me to look more in depth into this technosignature observation. And I have been running some atmospheric simulations, and this CFC realm has been an initial step as well. And I really appreciated Dr. Seeger's talk as well. So I'm really looking forward to including some additional trace gases as atmospheric technosignatures, and even moving beyond transits into IRXS and some other detection methods. And along with my colleague Colin Harrison, I think the machine learning advancement of collecting all this data that we're going to be receiving currently and in the future and looking into these unique transit light curves is really promising, an exciting field to get into.
All right. Well, thank you very much. So we do have plenty of time for questions then for our three speakers. So yes, give them a round of applause. And you're welcome to type into the Q&A if you'd like to. Just use the raise hand feature. We can also unmute your mic. So I'll just start a timer and wait a second. Not hearing any questions. So I mean, I really enjoy all your work. Okay, so I'll just, personal anecdote. When I started graduate school, I was promised that the terrestrial planet finder would launch in 2017, and we would have nice spectra of Earth-like planets, and we would be debating, whether there's oxygen and ozone and methane. So, here we are. I guess the ELT certainly is going to come online. Habitable World Observatory, I suspect will, but 2040s, I'm an American. I just know that this is going to get delayed. I'm hopeful that's not. But do you have any thoughts or reflections just on, thinking long term in our field? We're doing theoretical work for these big space telescopes and ground telescopes that are very much in all of our futures. So if you just have any thoughts about that.
I think for sure HAB worlds will be a huge step up, of course. The downside for HAB worlds, so to start with, the ELT, one of the limits we have is that even though it has this huge mirror, we are doing observations from the ground. So we always need to deal with our own atmosphere, and that really limits the number of targets we can actually look at. And so the number of rocky exoplanets we can truly observe with the ELT is very limited. HAB world should be able to allow us to really broaden this sample and look at more species, more planets. But the downside is that, as far as I know at the moment, there isn't that much focus on high-res spectroscopy on HAB worlds. We don't have high-res in space yet. So I think the ultimate next step would be to have something with a high resolution in space.
Yeah, thank you for that. That was something new I learned from your poster. I didn't realize that was a capability of the ELT. So that's really exciting. Yeah. Benji.
Yeah. So another study that I'm involved with right now is trying to see how good HAB worlds would be at the kind of thing that I did with HARPS. So looking for lasers from the reflectance spectra of exoplanets, and using things like HAB worlds. And you have a bit of a trade-off because it is lower resolution. But on the other hand, what makes it really exciting is that the coronagraph is taking out all of the starlight. And that means you have almost no background that a laser has to compete with. And so, from the standpoint of optical SETI of what I do, looking for laser communications, it it my earliest estimates are showing that it would allow for a lot more sensitivity than's been previously possible, simply because instead of a star that the laser has to outshine, it's just the reflected light of a planet, and that is quite a game changer. So I'm very excited.
Okay, thank you. Cal, if you have any thoughts, if not, I don't see any questions.
Great. For myself, then, I guess, as a response to Benjamin, one of the instruments that might be interesting to you then as well on the ELT will be Harmony, which also has a coronagraph, so it should be able to block out the light of the star, and it is operating in this optical to near infrared wavelength range. So that is one of those instruments that might have similar capabilities, which might be interesting to you.
Or even better, maybe. Yeah.
Maybe, though you will have to wait a little bit longer. I think the development has been delayed slightly, so 2035-ish should be, I think, something like that.
Cool.
And we got a question for Benjamin. Are you looking at Cherenkov telescope array possibilities?
No, but that's certainly a possibility. I mean, I believe there have already been some other optical SETI searches that have leveraged those or tried to piggyback off of what the Cherenkov telescopes are doing. So, yeah, I mean, that's another avenue for sure.
And then David Clements asked, would very high resolution spectroscopy at longer wavelengths, such as far IR with LETO, be of interest for SETI searches?
So, like he was saying, like further into the infrared, kind of, if I understood.
That's right.
Yeah, definitely. I mean, optical SETI is a bit of a funny phrase because when people say optical, they mean anything with a shorter wavelength than radio, which is more than optical, right? That does also include the infrared, and you do get a lot of the same communicative advantages of that because infrared is still shorter than radio. You still get the information advantage, the bits per second advantage over radio that allows. So yeah, searches for infrared lasers are a great idea, and there's also reasons why, because of how the interstellar medium scatters light, you might prefer an infrared laser over an optical laser. So yeah, absolutely, that's another promising vector for the field. Definitely.
And Benji, what are some natural explanations for your anomalies?
Well, so that's kind of the question that I'm trying to answer. I mean, so far we've ruled out a lot of natural explanations. We've ruled out, again, atmospheric air glow. We've ruled out a lot of different types of stellar emission lines. We haven't totally ruled those out because, these are red dwarf, relatively cooler types of stars, which means, less thermal Doppler broadening, so they can kind of mimic a laser in a lot of ways. But most recently, I showed it to someone else at I've been showing it to other people at Goddard who are specialists in red dwarf at chromospheres. And so far, we're coming up empty as far as getting an exact match to this candidate. So, we've been, I've colleague Sarah Peacock did a simulation of the chromosphere and found that given the chemical composition and temperature, she couldn't reproduce an emission line in that in that simulation that matched what I found. And then we also looked at a very magnetically active star, or rather, it was another colleague that had this idea and that did this. And we found that this is very magnetically active. This should have been flaring at all wavelengths if it was going to. And again, there was no emission that matched the wavelength of our candidate. So far, the tentative results that I've just gotten in the past month or so are kind of pointing away from stellar activity, and then with cosmic rays, we've already done a lot to rule those out, but there's still more to do because you can always have one striking at a weird angle. But I don't think cosmic rays are likely because we have found some other occurrences at the same wavelength at other observation times, which odds of a cosmic ray striking multiple times are very low. So right now it is an anomaly in the sense that it doesn't fit most of the natural hypotheses we've thrown at it. We also looked at, interference from LiDAR satellites, interference from ground-based adaptive optics lasers from neighboring observatories, and it doesn't match the wavelengths of those either. Now, that doesn't mean that what I found is a definitive alien technosignature. I'm not making any grandiose claim. All I'm saying is that it is an anomaly, and that's where you always want to be in this field. So, yep.
No, thank you. That's very great. So, all right. Well, thank you to our panelists again. Really enjoyed hearing about this. So, a round of applause, and we'll move on to Diana and Angelica. So, Diana, I think Angelica's here. I think Diana's here too. Yep, there she is. Perfect. All right. So Diana, feel free to get started. Go right ahead.
Hey there. Sure. Yeah, I wasn't sure of the format of this, to be honest, so I'm just gonna wing it, honestly.
Yep, you got 3 minutes.
I'm Diana.
Tell us anything you want.
Oh, yeah, cool. Yeah, I'm Diana. I'm a third-year PhD student. I'm at Cornell University. The past couple years, I've been basically propagating the motion of these stars in our solar neighborhood, so within 100 parsecs of us, using kinematic data from the Gaia satellite, and essentially figuring out where they land in the past and future, 500,000 years, and then seeing like which stars enter the Earth transit zone. So the Earth transit zone, if you're not familiar with that, it's a very narrow region in space, mapped out to a very narrow strip along the ecliptic in our sky. If which a star enters that zone, they're able to see our Earth transit our sun from their point of view, basically. So it's a pretty interesting idea. It's been around since the 80s, starting with some Soviet astrophysicists who published like the first list of stars crossing the ecliptic, and then in fast forward a couple of decades later, 2016, Renee Heller and I forgot his collaborator's name, but they published basically the modern definition of the Earth transit zone, which is defined as within basically half a degree overlying the ecliptic. Right. So I've propagating the motion of all these stars, and this time with a focus on exoplanet host stars, and I found 360 exoplanet host stars that enter the Earth transit zone within the past and future 500,000 years. So that's about orbiting these stars, or over 500 exoplanets, nearly 600 actually, so a 570, that's about the number I'm at right now. And what's more, after calculating their potential habitability of these exoplanets, I found that a minimum of 40 up to 87 planets in the habitable zone are orbiting these stars that can see as transit. So it's a really cool idea, really interesting prospect. My video poster has a bit more details, and yeah, the poster PDF, it's honestly kind of like a mini paper with lots more details in it, so definitely check that out if you want. And yeah, that's basically it.
All right. Thank you so much. Appreciate it. Angelica, the floor is yours.
Hello, we are the Vera C. Rubin Observatory Legacy Survey of Space and Time LSST for astrobiology and technosignatures, the first true movie camera for the universe and the new kid on the block among astronomical surveys. This work is carried out by 4 talented female undergraduate students from the University of Kent, the United Kingdom, who ask simple question: when LSST begins observing the universe every night, how will we recognize something truly new? For 10 years, LSST will scan the entire sky every few nights. Stars will brighten and fade, asteroids will drift, galaxies will interact, explosions will appear and disappear. And instead of isolated snapshots, we will have something fundamentally new, that is 10-year movie of the universe. And when you watch a movie, instead of snapshots, something remarkable happens. You begin to see the patterns. Every object LSST observes will be described by multiple observables and their relationships to millions of other objects and to other surveys data. These observables define what we can think of as the observational manifold of the known universe, a vast landscape. Each point of that landscape represents the object defined by the properties, and real physics creates structures. For example, stars occupy one mountain range, quasars another, variable stars trace characteristic paths across the terrain, and unstructured information like noise will scatter points randomly across this landscape. Now imagine shining light across that landscape. Instead of looking only at the mountains and valleys and paths, we also see the shadows they cast. Those shadows reveal relations between features of the landscape that are not immediately visible, and in math, this corresponds to the dual space of the manifold, an orthogonal perspective out of dimension of the landscape where relations between observables become visible. And sometimes the most interesting discoveries appear not on the landscape itself, but in the shadows, much like Sir Isaac Newton thinking under the shadow of the apple tree. If technological activity exists, it might appear as single strange measurement and would emerge as a coherent pattern in the data, perhaps not on the familiar terrain of known phenomena, but in the shadows of that manifold. University Kent students explore how LSST photometry and time domain behavior can define that manifold of known objects and how to look into the shadows. In other words, LSST will not simply give us more astronomical data or movie, it will also reveal its shadows, where we may discover phenomena we have never imagined before. Thank you.
All right, thank you very much. Do we have any questions for either of our presenters? It looks like there's a comment, but that's on optical lasers. I think that was the previous one. I'll just leave the comment there. No, I mean, I'm excited about what LSST is going to teach us. Diana, this is more of a comment, and if you just have any thoughts on this, obviously we learn a lot about exoplanets from the transit method. One of my colleagues pointed out to me, transits are accidental, and of course, if you have an accident of nature, just in the sense that it's serendipitous that you have this alignment. And so, if you have this alignment, of course, we're going to use it. But he pointed out that this was Stephen Kane that transits were never supposed to be our primary means of exoplanet discovery and characterization, and direct detection is where we're really headed in the future. And so. I just wonder if you've thought at all, since we're thinking about technosignatures, is the transit zone something that's interesting to us now in sort of a short term because of our technological limitations and our inability to do direct detection? And then so conversely, the extraterrestrials that would be observing us in transit might, sort of have similar limitations, or maybe, or do you think that even when we have very sophisticated direct detections, that there's still advantages to looking in the transit zone? Oh, and I should have turned my camera on. Sorry.
Yeah, so those are a pretty interesting set of questions, to be honest. Like in the first place, the transit method, like it has a very specific set of geometric conditions. Like for example, we're most able to see, we have to see like targets like edge on practically, otherwise we'll like miss it. So that's also like another constraint on this whole idea. But honestly, transits are relative transit methods. The transit method is relatively cheap, so that's like another like advantage. Like you can do it with ground-based telescopes if you really wanted to, for example. But yeah, I guess the work that I've been doing it doesn't necessarily assume anything technological about a potential extraterrestrial observer. It's just purely geometric. So it might be that if they're like some sort of like external observer out there, is like they call it, because I know that there's been discussion in the Slack about like the use of the civilization word, but if they were like, for example, like on a similar technological level as us, like they might also be that means like the transit method would also be cheap for them. So they might also do these like mass surveys like we've been doing with like Kepler and TESS and like other telescopes. So on one, but also that assumes like they're following like the same tech tree essentially as we are. Yeah, there are a lot of assumptions like based like that can be baked into that. But I guess like the beauty of like the ETZ method is that it's works purely like geometrically, so it's a good like first pass on for us determining these like list of like potentially interesting techno-signature targets. But yeah, those are all like really good questions you posed.
Yeah, no, thank you for that. It's a very speculative question, so I appreciate your answers. That was great.
No
And
problem.
then we have a question from Valentin Ivanov. Knowing Earth and that we are here opens the door for coordinated SETI, given the distance is known well enough. Have you thought about this possibility? I'm not sure I fully understand, but if either you want to respond to that.
Yeah, I could tackle that. So I'm assuming the coordinate SETI, do you mean like, I'm guessing you mean like we sent a message and the answer back or like back
I
and
see.
forth. Like I think that's what they mean.
Oh, so messaging within the transit zone.
Yeah, I think so. So I've definitely thought about it. You would definitely have to account for like light travel time, for example. And we do know the distance of these stars well enough. Gaia has given like pretty good like astrometric measurements on their parallax and radial velocity. The latter, which is like really important. It turns out like during our while we're doing this is that if you don't include the radial velocity when calculating the stellar motions, you actually like lose out on a couple stars that enter the ETZ. So you need a complete picture of the stellar like motion kinematics to like get an accurate gauge of like what stars like enter this area. But yeah, so it is pretty interesting because like it lets it factor in timing when we consider these targets to look at. For example, in the previous paper on this work, the 2021 paper by Lisa Calderon and Jackie Faherty, TRAPPIST-1 was one of the exoplanet host stars they found in the ETZ. So that enters the ETZ in about, I think, 16 years from now. They said 29 years back in 2021, so actually be more like 24, I think. But if you really wanted to, you could, if someone were really motivated to, they could potentially like, I don't know, like beam a message out there within like 20 so years from now and then like check back in like who knows who knows how long, a couple years to see if there's like a reply back. So I'm receiving another message about what's the time scale over which stars are in the transit zone. So it varies. A lot of it has to do with how fast these stars are moving. So some are in there for thousands of years. Some are in there for like only hundreds of years. It depends. The average number seems to be about 4,000 years, something like that. That's like a really ballpark estimate, though. I have to like check again. But some of these stars are in there for like a really long time. Some stars we found were across the past and future 500,000 years. At the end of the 500,000 years, they're still in the Earth transit zone. So for some of these stars, we have to like basically run the simulation for like longer time periods and farther distances to get like even more complete picture of like these like really long residing stars, if that makes sense.
Oh, thank you. Very fascinating. Okay, well, we should move on to the next set of speakers. So let's thank our presenters again, and we will move on. So we will go to Miles, Aamon, and we will add Gunay into this session as well because Evelina Kadiri had to cancel. So we will move three Miles, Aamon, and Gunay into our panelists, and we will start with Miles.
Yeah, thanks. So I'm an early career fellow at the Collegium Helveticum, which is the Institute for Advanced Study at ETH in Zurich, Switzerland. And basically what I've been looking at is how difficult is it to achieve spaceflight and sustain spaceflight from different homeworlds, so from different planets. And one of the early work that I saw on this was by, I think, Michael Hipka back in 2018, I want to say, and had basically pointed out that as you go to higher masses like super Earths, it gets more, progressively more difficult to basically get up out of the gravity well. But what I've been looking at is actually a couple of the parameters of the planets that make it more difficult, including the atmosphere. So basically the fraction of the atmosphere and the density you have around sea level, like very much determines how fast the rocket can go early on. And the slower the rocket goes, the more the gravity losses compound. And so it just progressively makes it much more difficult to actually get into space. And then also rotation is a big player because when you get into space, you kind of need something to do. We have geosynchronous orbit, we have sun synchronous orbit, and all of those things more or less depend on how fast our planet is rotating. And we also have a nearby moon. So in short, basically what I'm looking at from the planetary perspective is how hard is it to get into space? And once you get there, what is there actually to do? Which useful orbits do you have? And then I'll just say to end that I'm also looking at interplanetary space flight and just, given the transit windows and the average distance between planets, which planetary systems are more attractive for space flight. And I think I'll leave it there for now, but I'm really happy to exchange on this topic because I think it's received very little research.
All right, excellent. Thank you, Miles. Aamon.
Hi there, Jacob. Long time no see or hear. I work for Space Exploration, which is a space communications company. My colleague Eric Rowe that I do the research on, we're looking for unusual technosignatures around the Earth from 3 databases. Can you see me still? I wasn't too sure.
Yeah, we can see you and hear you.
Okay, great. From 3 databases extracting about 500 million reports since the 1940s. And we've established databases that provide the radar, thermal, and visual data where we have performance and reliability in unusual phenomena. And we've disregarded all natural and conventional known data that doesn't fit any conventional categories, and it leaves a phenomena that's categorized as unidentified aerial phenomena or UAP. What we have found is extremely interesting. That indicates that the UAP negates any known natural state of matter, that is the cause, but indicates possible technosignatures around the Earth. And this research has prompted us to explore a possible monitoring hypothesis around the Earth. However, in order for the hypothesis to be viable, we've set up a number of elements to support this proposition. So from the background of the research, we're aware of the transient nature of the UAP, and it has been a scientific problem for scientists to be able to carry out any useful astrophysical research to discover new knowledge. So the transient nature of the UAP events and the unpredictability about when and where the next event will happen is likely one of the main reasons why UAP have not been taken seriously by the scientific community. So we're proposing a hypothesis of a model that may demonstrate potential events happening when a controlled AI-type monitoring of the Earth is applied by using yet undiscovered intersections of orbital tracks at specific locations would provide the opportunity of testing the theory at multiple locations favorable for such events to take place. So from the observations on the ground, we've discovered a global pattern to UAP events, negating any known natural state of matter, that is the cause, with a pattern suggesting that UAP are technosignatures around the Earth, with a discovered orbital period of 66 minutes and undiscovered inclinations when synchronized with the rotation of the Earth. We have a Python code that was developed to find these patterns in the UAP data that could suggest repetitive behaviors, clustering tendencies, or periodic movement. So drawing potential parallels to pseudo-orbital mechanics in a simplified form. Work is in progress to discover yet these intersections of orbital tracks at specific locations at specific times, and this would provide the opportunity of testing the theory at multiple locations favourable for such events to take place. So from the observations in high altitudes, Beatrice Vallerol's research demonstrates transients have been discovered at artificial objects, either in high altitude orbits around the Earth or at high altitudes within the atmosphere. So some transients could potentially be UAP in Earth orbit that, if descending into the atmosphere, have demonstrated high velocity delivery. The Nimitz case is a good example of that. Our analysis using the Python code determined an orbital period, as I mentioned, based on the ground observations of 66 minutes. So the Python code was developed to perform all this analysis. We also analysed UAP propulsion based on high altitude operations, which lends to have a spacecraft powered thrust of equivalent of 160,000 kilowatts per hour per day, and more to sustain these particular orbits. Another colleague, Robert Powell, supports our analysis with a case study of a UAP at low altitude to have similar propulsion power source.
We are at time right now.
Oh, right. Oh, okay. Anyway, speculate that UAP may have fixed orbital tracks where it delivers probes on the same orbital track and so forth. Anyway, that's sorry, I went over time.
Yeah, no, that's all right. We'll move. No, thank you. That's very interesting, and we'll move on to Gunay's talk, and then we'll have some time for questions too. I see Jill's already typed in one, but no, sure. Thank you, Eamon, and Gunay, please, the floor is yours.
Hello, I am Günay Aliyeva. I am from Azerbaijan, and today I will present a new perspective on searching for a technosignature. Let's start with questions. Do we always need huge metal antennas and expensive sensors to find traces of alien technology in the universe? Could there be natural alternative? My topic, detecting technosignature using plant biosignals. Plants do not have a nervous system like animals, but evolution has given them a complex network of electrical signals. When a plant senses any external stimulus, touch, chemicals, light, electromagnetic changes, or temperature, it immediately produced bioelectrical signals. These signals can be measured using extinct methods. Mimosa pudica is a clear example. When it is touched, calcium ions inside its cells increase and spread throughout the plant within seconds. This causes its leaves to fold. You can clearly see this is my video poster. Why plant? Plants are immobile and can collect long-term physiological information from a single point. Their use environmental sensors has already been studied. Also, measuring plant bioelectrical signals helps detect damage or disease before it starts. recording crop loss. I suggest using plant biosignals in a new way. We might detect signals from advanced civilization that could reach our planet through plant bioelectrical signals. These signals have not been recorded yet, but if they exist, maybe they are adapted to living systems, not our technology. Methodology. Plants with high bioelectrical activity are selected, planted in large areas, and monitored for environmental changes. Results are analyzed with artificial intelligence, AI. Any anomaly allows us to investigate its source. This method can strongly support current SETI technologies. Plants get their energy from sunlight, are environmentally safe, and produce no waste. Despite challenges, the future technosignatures sensors may grow in forest, not laboratories. By listening to the silent language of nature, we can explore into universe in a more ecological and gentle way. These concepts
We are at
combine.
time as well. But
Sorry.
if you have a finishing thought, please conclude your thought.
Okay. This concept combines astrology, biology, biotechnology, and AI, offering a new perspective. Please send your questions in writing, and I will answer them in detail in writing. I have language limitations. Thank you for your understanding.
Thank you very much. No, your English is fantastic, and I appreciate you joining us here. Okay, great. So we have some time for questions. So we'll start. I see Jill typed in a question for Amon. So Amon, you're using known databases. Could your events come from classified activity?
No, these are open source databases. There's at least 4 of them anyway, mainly in the US and in Europe.
Okay, I mean, I think the idea is the anomalies, could they reflect classified events?
Oh, yes, we've taken that in consideration. And in fact, what's interesting here is that we've traced reports going way back to the 1880s with similar type of constructs. So that negates any, classified objects from whatever, 30s, 40s, or 50s.
Thank you. So we have a question for Gune. So Jill asks, is the strength of plant signals great enough to see over interstellar distances? And Diana asks a related question. So when plants release electrical signals, do they release certain chemicals? How feasible a biosignature marker might be in addition to technosignature? And if you'd prefer to respond to that in writing, that's okay too.
I will answer in writing.
Okay, no problem. Yeah, no, it's very interesting. I was wondering the same thing. But yeah, we'll wait for your response there. A question for Miles from Caleb. There was a recent study applying computer models developed for modeling island colonization in the Pacific to colonizing nearby stars. Have you thought of using a similar approach?
Yeah, great question. I mean, I think as well, there was a recent paper that went up on Archive like a week ago by Caleb Scharf, actually applying this model maybe with an economic layer applied to it for like interplanetary settlement and I guess trade. But I think it's also interesting to talk about like the interstellar aspect as well. So this would be also a very interesting kind of like add-on to the orbital interplanetary and then interstellar kind of like model. But I haven't really got that far to really think about the interstellar aspects yet. But it's a good direction, I think.
Great. And Benji asked a question for Aemon. Have you derived the orbital period pattern, just timing between reports, observations across the world, or something else? Also, have you been able to use the pattern to time your observations and see a UAP showing up at the predicted time?
Yeah, good one. We've highly, how should I put it? The timing has been very important with the reports. The more accurate the timing, the better for the actual model to work. And on the second question there, yes, we actually did test it out for the very first time there in December. And to actually prove it, we actually had national television at it. I actually asked them would they come and just in case it would happen, and sure enough it did. This will be actually shown this year in a documentary. So we actually had 6 objects actually did turn up. So it is predictable, we'll put it that way.
Very interesting. Okay, well, thank you all to our presenters. Thanks once again, and we'll move on to our final group of speakers. We have Robin and Anna Maria, and then please, of course, continue the conversation in Slack or in the chat here during the session. So thank you again. And Robin, we will start with you.
Okay, great. Thanks very much. So my name's Robin Corbett. I'm a high-energy astrophysicist at the NASA Goddard Space Flight Center and UMBC. The title of my poster is A Less Terrifying Universe, Mundanity as an Explanation for the Fermi Paradox. This recently appeared in the Open Journal of Astrophysics, and you can find more details there. So the title refers to the quote attributed to Arthur C. Clarke. 2 possibilities exist. Either we are alone in the universe or we are not. Both are equally terrifying. And the goal of my work is to try to consider non-terrifying solutions to the Fermi paradox. Now, there have been a number of explanations put forward, of course, and they tend to be rather exotic, dramatic. That, for example, there's a great filter wanting to destroy us, or we're living in a zoo, something like that. So in the mundane perspective, we take that the most mundane explanation, if physically feasible, is most likely to be correct. So essentially Occam's razor. And also from the Copernican mediocrity principle, humanity does not occupy a special place in the universe. So the principles are, we're not alone. If we were unique, that wouldn't be mundane. Also, there is a limit to technology development. Now, the ETCs are more advanced than us, but they've reached some sort of technology plateau. They don't have a dramatic leap. Nothing equivalent to harnessing electricity. Dark matter and dark energy are not useful for new technology. There's also a modest number of ETCs in the Milky Way at this plateau level, maybe 10 to the 4, 10 to the 5. Now, if you're exploring the galaxy with von Neumann probes, the benefits you get are the information which is sent back to you. But there are also potential risks. The fear of probes going rogue. That's not very mundane, but the fear of this is something which is being thought about on the Earth. So you have a growing, diminishing benefit, meeting new civilizations, and you have increasing fear and boredom. So this is kind of a damped exploration of the galaxy. So the implications of this are, we can explain the Fermi paradox if the galaxy contains a modest number of technological civilizations, much less than the Kardashev 2 level. So there's no long-duration high-power beacons, no Dyson spheres, no faster-than-light travel. But maybe you can find some leaky radiation on a relatively short timescale, historically speaking, less than 1,000 years. That'd be very profound. I mean, we may still be a bit disappointed. Also, life in general could be common, so maybe HWO or life could detect biosignatures. Thanks very much. Please see my poster on my paper.
All right. Thank you so much, Robin. And we will conclude with Anna Maria and then some questions.
Right. Thank you, Jacob. Let me start my timer. Okay, so
I'm an associate professor of computational and data sciences at George Mason University. The poster that I submitted is actually in line with what Olivia just presented earlier. So this is an idea that spurred out of the Dyson's Minds workshop, and it's about the P versus NP computational paradigms. So P versus NP is one of the most important conjectures in computational complexity in computer science and information theory. It's basically one of the 10 big millennial problems. And it posits that computational time for any algorithm increases with a polynomial function of the input size into that function. So P versus NP basically does not depend on the nature of computation, whether it's binary, whether it's quantum, whether it's biological, whether it's based on RNA, and so on, whatever we can consider as computation. And it also doesn't depend on technology, which is very interesting, but only depends on the time it takes to manage, transform, and produce information with a universal computer, whether this universal computer is a universal Turing machine or a computational device such as RNA, DNA, crystals, and so on. And the P versus NP paradigm has implications for technosignatures and SETI twofold. First, assuming that any other long civilization in the universe other than our own has developed technology, this technology is computable, regardless of the nature of computation. So this implies that P versus NP is more likely to hold for any other technological advanced civilization in the universe, which directly implies that there are inherent universal computational limits to technological growth anywhere. So if we can assess which are these upper bound limits to technological growth, we can infer afterwards the implications for detection and observability of the technosignatures that might have reached or approached these limits. And secondfold, the P versus NP problem can also be reflected directly on the search for technosignatures. And we posit that searching for technosignatures is essentially an NP hard problem. And I cannot detail that right now, but this means that we cannot solve it within given polynomial time unless we find a universal key to the problem and reduce the polynomial time for all NP hard problems, therefore transforming them into NP complete problems. So we also posit that such a universal key cannot be found computationally or within the current framework of computational complexity theory, but can potentially be found using the physics of time and the relationship between information, energy, and time. Thank you.
Okay, thank you. Thank you to both our speakers. And we have some time for questions if anybody wants to type them in. So Anna Maria, I think I saw that you were at the Dyson Minds workshop from the presentation earlier. Is that right? So the question I have for you is, do you think that there are, large scale limits to computation? The question I ask is, what do you do with all this energy? And so that's sort of one question is, if you can harness the energy, is there a reason to? But maybe are there limits to how much energy one can even attempt to harness or utilize?
Yeah, so that's a good question. I didn't think about the energy per se, because that's a little bit out of my realm. So I've only thought about informational limits, right? And I know there is a correspondence between information and energy that we need the astrophysicists, who are more familiar with space-time and those really hard paradigms from physics to think about the relationship between information and energy. But we do know that there are limits to information in the universe, and that it's possible that some computational time to be longer than the universal cosmological time for how long the universe is going to last. So.
Thank you. All right, well, I don't see any other questions. Then I'm going to pose one to Robin. So Robin, if we live in a mundane universe, we're not going to find Dyson spheres, we're not going to find beacons. What does this mean for our future? Does this mean that any future human trajectory we imagine that ends up with Dyson spheres is probably fraught with problems we haven't thought about, and that it's not does this have any implications for imagining these kind of futures for ourselves?
I'm kind of thinking that this has to be something which would apply to any civilization, to use the C word. But there's a balance between this cost-benefit analysis, cost and reward, and it's very difficult to make a Dyson sphere. And as you were referring to before, there could be a limit to the utility of energy, that you stop getting a big benefit for it. So there's not really either the motivation and quite probably not the means to be able to construct a very large scale a Dyson sphere or swarm.
All right, thank you. All right, I'll pause just for another moment. Anybody has any other questions or comments? But this has been a really great poster session. Thanks to everybody, all the presenters, everybody asking questions. Okay, hearing none, then we'll bring this session to a close. So let's give a round of applause to Robin and Maria, but then all of our speakers. Thank you again.